Well, here we are. So today I'm going to talk about section 4.2. Now I realize you're wondering what happened to section 4.1, and I'm going to be honest with you, I skipped it. We may come back and pick that up. We may not come back and pick that up. It's kind of an esoteric section. It doesn't really connect to a lot of other things that we work on, and it doesn't really apply directly to what happens in Calc 2. So given the current stated situation, I thought perhaps we would just begin with the more applicable sections. Now, I have several options planned in terms of recording videos for you guys. This is the first one. I'm using a document camera, white paper, black pen. It's going to phase in and out in terms of focus. It's going to, but once we push the pause button, when we have it focused on our screen, we'll be able to catch up. Obviously, if I talk too fast, you can push the pause button, and then I'll be interested in any feedback you're willing to give me. I'll be using, just send me an email and say, well, that was a disaster, Kevin. We expected that from you. Or, hey, that worked out okay. That was a surprise. We didn't expect that from you. Whichever way you want to go with this. So, I'm going to do this lecture this way. I have, like I said, I have a couple other plans in place. I'll do the next lecture differently. And then I have a third plan in place, and we'll do the third lecture using the third plan, and then we'll adapt. That's what we're going to do here, right? We're just going to adapt. So today we're going to talk about, or now, I don't know if it's today where you are. I guess it's today everywhere, isn't it? All right, here we go. That's enough of the tangents. Oh, and Kylie, I put on lotion, so I don't have any dry skin for you there. I knew that'd be. And look, no nails. All right, so here we go. We're going to talk about maximum and minimum values of functions. That's what today's lesson is about. We'd like to be able to figure out where a function has a max and where a function has a min, because in the real world we use functions for things like, mapping revenue, mapping profit, mapping the heat that goes through an engine, and we would like high tide, for example, another function. So we would like to know where the maximum and the minimum values are going to occur. So we're going to talk about how to find maximums and minimums of functions. All right. Now, we're going to start with some definitions because we have to have these definitions in place before I can actually move into how to find them. The important thing about these definitions is I'm going to present 4 definitions. I'm going to present the definition of an absolute maximum. I'm going to present the definition of an absolute minimum. I'm going to present the definition of a local maximum, and I'm going to present the definition of a local minimum. The most important thing we need to know about these: all min and max definitions are unrelated. Now, what do I mean by that? What I mean by that is it is very typical for us to look at these definitions and then try to construct associations between them in the context of, we say, oh, okay, if I have a local min, then I must, and then we connect something to the end of that sentence. Something such as, if I have a local min, I must have a local max. Or we may say, if I have an absolute maximum, well, then I must have an absolute minimum. We could say something like, if I have an absolute minimum, well, then I must have a local minimum as well. The important thing for us to understand is that while they look similar, these are 4 distinct and standalone definitions. One in existence, meaning if I have an absolute max, that does not imply that I have an absolute min. If I have a local min, there's no connection that says I automatically have one of the other 3. So I like to start by making sure everybody understands that when we check for these 4 things, we check for these 4 things individually. All right? It's 4 unique exercises. So let's start with the definitions. if we let C be a number in the domain of a function. Then f of c is called. And we're going to have two options here. We're going to start with an absolute maximum. When is f of c, now please notice this is the y value, right? That's the y value. When is the y value going to be referred to as an absolute maximum? Well, it's going to be referred to as an absolute maximum if f of c is greater than or equal to f of x for all x in the, that's not how you spell that, is it? Domain. All right? So if our y value is the largest y value, then we refer to that as an absolute maximum. It is clearly the biggest point in terms of y. It is the largest y value. If we're looking at the graph, it is the tallest point on the graph. It is where the graph reaches its apex, if we want to think about it that way. Now, there's no guarantee that we're only going to have one absolute maximum. If you have a parabola that opens down, yeah, you're going to have one absolute max. It's going to be right there. But if you have your friend the sine curve, the sine curve has an infinite number of absolute maximums. So the context that we need to keep in mind here when talking about an absolute max is, yes, it's the largest y value, but there's no guarantee as to how many of them we're going to have. Right? We may not have an absolute max. We could easily have a function, right? Let's just stick with polynomials. We could have a function that's a parabola that opens up and just continues to open up forever. This function does not have an absolute max. Now, if you're thinking ahead, you're probably thinking, well, I bet it has an absolute min, and of course you're right, it does have an absolute min. Whereas this function right here, all right, this function does not have an absolute min because it goes down forever. Our friend sine has an infinite number of absolute minimums. So this is what I meant earlier when I was saying we have to address each of these definitions individually. All right? Just to complete our definition here, the definition for an absolute min, which I'll start by abbreviating. I wrote absolute max out, but from now on, we'll just save time and we'll abbreviate. The absolute min says, what you expect it to say. It says f of c is less than or equal to f of x for all x in the domain. And as we pointed out, sine has an absolute min here, it has an absolute min here, and it has an infinite number of absolute mins. This parabola, of course, has an absolute min right here. All right. Now, it's not necessary that a function has an absolute min. It's not necessary it has an absolute max. If we draw our graph of y equals e to the x, I miss my whiteboard and being able to erase all my mistakes. If we draw the graph y equals e to the x, well, that graph does not have an absolute max. It goes up and up and up and up and up forever. Nor does it have an absolute min, because if you look at the graph, yes, it has a horizontal asymptote at 0, but it never hits 0. So this graph never has an absolute min. There is no place where you can say that is the smallest y value, because if we continue to pick points on the x-axis in the domain of the function, which would be all the points on the x-axis, because this function is defined everywhere, but if we continue to pick points on the x-axis going to the left, we are going to continue to end up with smaller and smaller and smaller y values. And if that happens, then we can't say that that is the smallest y value, and therefore we cannot say that this function has an absolute min. So that's our definition of absolute max and absolute mins. Now we have a related definition to that, right? We have a definition that's related in the context of it has the same words, not related in the context of it has the same definition. All right, so let's add that to our list of definitions, and then we can start doing some more of these definite examples, so we can, perhaps get our hands wrapped around this idea of what is an absolute max and what is an absolute min. Hey, by the way, I didn't mention this at the beginning, but it wouldn't hurt to be following along in your book while I'm giving the lesson. So, where do we go from here? Well, we'll add our definition of a local, right? That's what we're going to say here. This definition is going to be a local maximum and a local minimum. And it says this. It says the number f of c is a, and then we have two options here as well. We're going to call it a local maximum value of f if f of c is greater than or equal to f of x. Now that looks very similar. I understand you've written that down and you're thinking to yourself, wait, that's almost essentially the same thing I wrote up here, and I agree, it's very similar. Similar, yes. The same, absolutely not. Ooh, pardon that little pun there, that was not intentional. All right. The most important part of the definition of a local maximum is what follows from here. Local maximum value of f if f of c is greater than or equal to f of x. And now we get an innocent sounding phrase. When x is near c. Now while that phrase sounds innocent, it is not. Right? It's not. What that phrase means is f of c must be, that's not b, must be the largest y value in an open interval. And I'm not going to use interval here. I'm going to use neighborhood, and we'll talk about that in just a second. In an open neighborhood about C. All right. Now that requires some explanation. What do we mean by an open neighborhood about C? Well, the simplest way for us to come to grips with what an open neighborhood is an open neighborhood is an open interval. Almost. It's an open interval that may or may not contain C. So for our sake, to make this as approachable as possible, I would suggest that we just think of it as an open neighborhood being an open interval. Okay? And I'm going to go through a myriad of examples here in a few minutes, and I'm going to do my best to make sure that we can differentiate between our local maximum and our absolute maximum, And then, in addition, of course, we haven't written it yet, but we're going to want to differentiate between our local minimum and our absolute minimum. So let's complete this by just filling in the definition for the local minimum. The local minimum says the number f of c is a local minimum value of f if f of c is less than or equal to f of x when, and here's the important part, of course, x is near c. Okay? So, those are our definitions, right? Those are our definitions. Those are 4 unique definitions. I recognize the similarities in what we have written. I recognize the similarities in what I've stated. But we have to start with the idea that these are unrelated. One does not imply the existence of the other. We don't have to have any of them. This function, while we have not done examples or drawn examples yet of local mins and maxes, this function right here, it does not have any of the 4. Right? It doesn't have a local min, it doesn't have a local max, it doesn't have an absolute min, nor does it have an absolute max. Whereas this function right here, the sine curve, right, the sine curve, has all 4 of them. As it turns out, each of these absolute maximums turns out to be a local maximum. Over here, this absolute maximum turns out to be a local maximum. So at this point, what I'm going to do is I'm just going to draw a lot of graphs and do my best to try to get you to come to grips with what do we mean by these definitions. All right? So I'm gonna remove this piece of paper. Obviously, you can hit the pause button at this point if you have something you need to copy down. I'm going to remove this piece of paper, move on to a new sheet, and on this sheet we're just going to draw some examples and try to see if we can indeed come to grips with how these definitions stand alone. All right? So let's start with just a function. And we'll start with something relatively simple. Let's start with just our upside down parabola again. When it comes to recognizing an absolute maximum value, most of us are pretty quick at doing that. We tend to be very successful at that. We look at this, we see that's the biggest y value on the graph. Therefore, that is the absolute max. And your instincts are 100% correct there. This is an absolute max. Now, how do I know if it's a local max? That's where we get into a little bit of discussion. Mentally, we're going to have a conversation with ourselves. If we want to convince ourselves that this is an absolute max, we need to come down here and we need to look at the associated x value. We're calling it c in our book. And then we need to put an open interval around c. And we have to ask ourselves, in this interval, I should mention at this point, when we talk about open intervals, we're talking about small intervals in terms of width. And we don't get to draw an interval from 6 to 2,504. That's not what we're talking about. We're talking about an interval whose width, by definition, is tiny. All right? Now, what do we ask ourselves here? Well, we have our definition that says if that is the largest y value out of any x's near c, then that is what we're going to call a local min. And so that's what we ask ourselves. We ask ourselves, is this the biggest y value out of any of the possible y values associated with any of the x values in our interval? And if we take a look at that, if we project one of these up here, we see this y value is here. Our vertex of our parabola is clearly a larger y value. And we say, okay, it's bigger than that. And if that holds for any y value we can pick in that interval, then we say that is also a local min. So while we've decided it's an absolute max, it's a completely separate conversation with ourselves to be able to say this is a local maximum. I'm sorry, I said local min a second ago, but I meant local max. So that is how the conversation has to take place. That is what we have to do in our analysis to determine the difference between an absolute max and a local max. And I understand right now it appears that one is the same as the other. But I'm going to draw another graph and we'll see that that's not the case. Let's just draw a graph that looks like this. We'll just make it a line segment and we'll put a dot right here. This is C. And we want to ask ourselves, is that an absolute max? And the answer is yes. Yes, it is. That is an absolute max. It's an absolute max because it's the biggest y value. And because it's the biggest y value in the domain, then it is an absolute max. All right? That dot is, this C is clearly in the domain of the function. We've got a functional value right here. And so clearly that is in the domain. We always have to check that. And so this is an absolute max. Things become a little less clear, however, when we ask ourselves if that's an if that's a local maximum. The definition is very specific, and we have to keep that in mind. The definition requires that we put an open interval around C and then decide, based on all the values within that interval, is that my biggest y value? Now, the important thing I said there was all the values within the interval. When you look at this x value right here, there is no associated y value that goes along with that. Open intervals have two sides, and in this case, one side of our open interval does not contain x values that result in corresponding y values. So I can't put an open interval around C, because when I do, I end up with this picture right here, and there is no y value that associates with that. Because of that fine point, we have to say this is not a local minimum. I keep saying that, and you know what I mean. I mean maximum. This is not a local maximum. If we were to put a dot here and say that just this line segment is our entire function, and we were to come up here and instead of calling this C, we'll call this D, this, in terms of absolute minimum, we have to say yes. This is an absolute minimum. It is the smallest y value out of all the y values associated with elements of the domain. However, this is not, for the same argument, by the same argument we used up here, if I put an open interval around here, there are points over here that are not associated with the graph. So in terms of a local minimum, we would have to say no. No, this is not a local minimum. All right? That's a fine point. It's one that takes a little while for us to come to grips with, but it's a very significant point. If we draw a parabola that opens like this but has a hole at the vertex, this parabola does not have a largest y value. There is no absolute max. None. There's not a largest y value. That hole would be our largest y value. Now, it's very common for us to think, wait a minute, hold on. The hole starts at C. That's where the hole is. F of C is undefined. I got that, Kevin. I can see F of C is undefined. However, there's a number right next to C on the x-axis. The real line is dense. There are numbers next to C. And so all I have to do is tell you, well, the absolute maximum is a number that comes, that's associated with the x value that's right next to C. The problem with that argument is you can't find the x value right next to c. There is no x value right next to c in the context of being definable as a number. When you find the x value right next to c, and you tell me, okay, this is it, this is the x value right next to c, I plugged it into the function, I have a y value, this is the largest y value. Me being me, I'm going to take your x value, all right, whatever it is, let's just call it x. I know that's not right next to c, but we're imagining here. I'm going to take your value that's right next to c, I'm going to add it to c, and I'm going to divide by 2, and now I'm going to find a value between your value and c, and I'm going to say, what about the y value associated with that? And then you're going to say, okay, we'll use that one, and of course we can play this game forever. There is no definable, in terms of a number, definable, like I can say this number is this. There is no number right next to c, and since I can't find that number, I have to conclude there is no absolute maximum. There's also no absolute minimum. Sorry, no local min. No local max. There's no local max there either. Now, is it possible to have a graph that doesn't have a local min, a local max, an absolute max, or an absolute min? Yes, it is. We've already drawn it on the previous page, but I'll draw it again. Any exponential curve like y equals e to the x, this graph has no, and under the no column, we would get absolute max, we would get absolute min, we would get local max, and we would get local min. This is what I was referring to a few minutes ago when I said they're not related in any shape, manner, or form, right? Other than they have similar symbols in their definitions. So this graph doesn't have any of the four. Now, it doesn't take a lot of work to draw a graph that has all of the four. We've already done that. Your sine curve has all four of these. So in terms of the sine curve, y equals sine x, and I won't draw the graph again, we can all imagine that in our heads. Y equals sine x, all four exist, and there are an infinite number of each. All right? Sine reaches a maximum, as we all know, at pi over 2. And so it also reaches a maximum, of course, at 3 pi over 2, and then again at 5 pi over 2, and 7 pi over 2. So every one of those values is a local max and a local min. It reaches its minimum at 3 pi over 2. So at 3 pi over 2, you're going to have a local min. Pardon me. The local maxes, of course, are going to be pi over 2 and then 5 pi over 2, because they're going to be off by the period of 2 pi. So you know what I mean. Now, where do we go from here? Well, we can draw one more graph that brings all of this, I hope, to a conclusion. I think we've had enough graphs. Hey, I'm getting a phone call. How exciting is that? So, what do we need to draw? Well, let's just draw a constant function, a function that goes like this, where we get y equals c. All right? And what do we know about this point? Well, that y value is greater than or equal to, that's the important thing. See, back in this definition, back here in the definition, you may not have paid a lot of attention to it as we were writing it down, but it was greater than or equal to, less than or equal to, greater than or equal to, less than or equal to. What does that tell us? Well, that tells us a situation such as this y value is c. But you know a funny thing, so is this one, so is this one, and so is this one, and so is this one. All those y values are c. So this y value is greater than or equal to all the y values. So that y value is an absolute max. But this y value is greater than or equal to all the y values. So that y value is an absolute max. And I think you see where this is going. Every point on this line is an absolute max. This y value is less than or equal to all the y values. This y value is also less than or equal to all the y values. So every y value on this line is an absolute min. And if we extend it, every y value is a local min, and every y value is a local max. Because I can put an open interval around here. We'll call this C1, so I don't have the same C's there. This y value is greater than or equal to every y value in this open interval, and therefore that is a local maximum. So sine has an infinite number of absolute maxes, the top of every hump. This graph has an infinite number of absolute maxes. Every single point is an absolute max. All right. So that's our discussion of the definitions of absolute mins and absolute maxes. Where do we go from here, and how is this going to morph into what we're going to do in the homework, right? The important question in a calculus class. Well, the next thing we're going to write down is a very important theorem. We're going to write down something called the extreme value theorem. Now, our quest, as I told you at the beginning of the video, our quest is to, oh, that's fun. Why, isn't that interesting? Maybe if I put my hand here, it'll stop. There we go. Sorry about that. So our quest here is to find these mins and maxes, and that's what we're looking for. So the extreme value theorem says this. It's the beginning of how do I go about finding these. It says if f is continuous, right? Now we got to remember what continuous means. Continuous means we can draw the graph without lifting our pencil. Continuous means no holes, no jumps, no vertical asymptotes. So if f is continuous on a closed interval, a to b. All right. So if f is continuous on a closed interval a to b, then the following is true. F attains an absolute max called f of c, and an absolute minimum called f of d at some numbers C and D within A to B. So what does that say? That says if you give me a function that's continuous, no holes, no jumps, no vertical asymptotes. If you give me a continuous function on a closed interval, then I must have an absolute min and I must have an absolute max. Now, I might have more than one, but I must have at least one. So how does this translate? Let's go straight to a function we've previously drawn. Let's go to our function y equals e to the x. All right? And we said, okay, this function has no local mins, has no local maxes, has no absolute mins, and has no absolute maxes. Oh, let me call attention to this here. I grabbed a blue pen to underline with. I don't know if you're going to be able to tell. You can't tell at all. So what do you care? This is talking about absolute mins and absolute maxes. All right? Absolute mins and absolute maxes only. It's not talking about local mins and local maxes. So how does this function change if I make the interval closed from A to B? All right. What happens if we close the interval from A to B? Well, if I close the interval from A to B, right, let's just put an A here. We'll put a B here. Now, this means our function is only this portion right here. This is what we're talking about. This is the portion of our function we're now talking about. By the way, when you give me your comments, you don't have to comment on the flashing light. I can see that happening. I'm not sure why it's happening now, but I think it's just because it just wants to frustrate me. So, it's all personal, right? What do I know about this graph? Well, this graph has an absolute min. It's right here. And this graph has an absolute max. It's right here. By allowing me to define this function on a closed interval only, closed at A, closed to B. Remember, this means A is less than or equal to X is less than or equal to B. Closed interval. I suddenly get an absolute max and an absolute min within that interval. Now, it could be the case, and it often is, you could have a function that goes like this, and then it comes down here like this, and then it goes like this, and let's just make it go over here like this. So we have this function, all right? Now, if we were just talking about the definition of an absolute max and the definition of an absolute min, we all know where the absolute max would be, and we would say this does not have an absolute min. But the extreme value theorem says, well, what happens if you put this, right, if you put this on a closed interval from A to B? Well, when we put things on a closed interval, and we only focus on the closed interval, we allow ourselves, right, to take what the behavior was for the general function and then say, well, I'm not going to focus on that. I'm going to focus on what happens in the closed interval. So we're only talking about this graph between here and between here. Now, by the theorem, it has to have an absolute max. It has to have an absolute min. It does. It does. We can see that this is the absolute max. Notice it's not the absolute max of the function. If we were defining the interval from negative infinity to infinity, the absolute max would clearly be here. But we're not doing that. What about the absolute min? Well, we have an absolute min now. Right? We didn't have one before, but now we do. Our absolute min is right here. Right? This is our absolute minimum. So when we were on the open interval from negative infinity to infinity, we didn't have an absolute minimum. But now we do. Okay? So that's the importance of the extreme value theorem. It forces us to have absolute mins and absolute maxes. So where do we go from here? Remember our quest. Our quest is, how do I find them? When I give you a function, I just write a function on the board in f of x notation, y equals notation. How are you going to go find the absolute min and the absolute max? Right? What are you going to do about finding those? Where are those going to come from? Well, we get a theorem here that's a hint. It's not the answer, it's a hint. It's called Fermat's theorem. That's not where the apostrophe goes, genius. So it's called Fermat's theorem. And the important thing for us to get in our heads when we write down Fermat's theorem is that this is not the answer to the question of how do I go find the absolute mins and the absolute maxes, or how do I go find the local mins and the local maxes. It's not the answer. It looks like it might be the answer, but if we pay attention to what we're writing, we quickly realize it's not the answer. It all starts with the word if right here. This says if f has a local max or min at C, and if f prime of C exists, then f prime of C equals 0. Now, as calculus students, we get so excited when we see this because we think, wherever the derivative is 0, that's it. That's what I'm looking for. The problem with the theorem is it's written in the wrong order. I mean, look at it closely. This is a conditional theorem. It says, if P, then Q, right? If P, then Q. The problem is, the if is what we want to be the then, and the then is what we want to be the if. It doesn't tell us, hey, when the derivative equals 0, you have a local min or a local max. Right? It doesn't say that. That's not what it says. And it says, if you have a local min or a local max, you already know it's there. So you've already found it. That's the if. You've already found it. Our problem is we don't know where they are. But this says if you've already found it, well, here's what you do. Well, what do I do if I haven't found it yet? Well, the theorem doesn't help us with that. It also has a couple of built-in problems, right? If you look at this function, we all know what this function looks like. Right, this function comes down here, and then it goes like this, and then it goes like this. And if we take the derivative of that, which is what a lot of us want to do, right? We read this, and I'm just going to take the derivative and set equals 0. That's the magic spot. No, it's not. If you take the derivative of this, you get 3x squared. If you set that equal to 0, f prime of x equals 0, when? Right? That's our question. And is that going to happen? Well, we all know when 3 times x squared equals 0. The answer is, right? The answer is when x equals 0. But if you look at this graph, that's not a local min. That's not a local max. It's neither. So Fermat's theorem comes with this temptation, I like to call it, of saying, well, if the derivative is 0, boom, local min or local max. That's not true. This derivative is 0 at 0, and it's not a local min or a local max. In addition to that, you notice me try to be cheap there and use the back side of the paper? It didn't really work out very well, did it? In addition to that, we have a function such as this one. Right? This is a simple function. This is f of x equals the absolute value of x. Right? I think I fixed it for the next 14 seconds. So this is the function f of x equals the absolute value of x. Well, what do we know about this function? Well, this is clearly a local min. But this is a corner. Now, why is that a big deal? I mean, it must be a big deal. I use an exclamation point. Why is that a big deal? Derivatives don't exist at corners. So if you were going to try to use Fermat's theorem and say, well, you know, whenever the derivative is 0, I get a local min or a local max, the problem you have is, here's a case where you clearly have a local min, but the derivative is not 0. The derivative doesn't even exist. Right? So what are we going to do here? Right? That's our question. What are we going to do? Well, we're going to move in a direction that's indicated by Fermat's theorem, and we're going to start by giving ourselves a definition. We're going to define something that's called a critical number. Now, they must be important. I mean, look at that definition. It's called the critical number. A critical number of a function f is a number c in the domain. I kind of snickered. I apologize. I mean, you're not here, so you don't know why I snickered. But I snickered because this is the important part. All right, don't forget that. Don't forget that. So if you have a critical number, it's got to be in the domain. We're gonna come up here just in a second with a way to find critical numbers, and it's not going to be complicated. And it's not complicated. There's nothing about it that's complicated. But what we do what can I do to mess this up on the test? It doesn't look that hard, so what am I going to do to mess it up? Well, one of the things you can do to mess it up is you can go find me critical numbers who aren't in the domain. Because the test to determine what a critical number is doesn't include a step where it says, hey, check to see if I'm in the domain. You and we have to remember to do that. Right? That's our responsibility. So I pause here in writing the definition to call attention to a critical number of a function f is a number c in the domain of f such that either f prime of c equals 0, so the derivative equals 0, or f prime of c does not exist. All right. Those two places are where you and I are going to go to look for mins and maxes. We're going to look for mins and maxes on those values that we have now given a name. Those values that are critical numbers. That's where we're going to go look for mins and maxes. Out of everything in the domain of the function, we're going to eliminate everybody as a possible min or max, local min or max. I'm not sure what just happened. So I think we're still here. We're still recording. So my whole computer screen went black. I kind of went into panic mode there for a second. Sorry. So we're going to look for local mins and maxes at these points. Okay. So now we're going to get a rule. It's not even a theorem in our book. It's just a statement. Doesn't even put it in bold. He puts it in a box. He says if f has a local min or max at C, then C is a critical number. Of F. All right. So we've gotten to the answer. It's taken a while. By my clock, 48 minutes and 33 seconds. But we've gotten there. What do I do, Kevin, to go find a local min or a local max? We're going to take the derivative. We're going to set it equal to 0. And we're going to see where it fails to exist. And then we're going to test those. There's no guarantee those are going to be local mins or local maxes. We're going to test those. And we're going to determine if they're local mins or local maxes. Okay? Now, at this point, we take a bit of a tangent. It's not a huge tangent, but it's a bit of a tangent. Mr. Stewart takes a small tangent here, and he says, okay, we're going to talk about something called the closed interval method. Now, the reason he's taking a tangent here is because he's given it to us. He's given us the answer. The answer has been presented. We have it. It's right here in front of us. If we want to find a local min or a local max, local keyword here, local. If we want to find a local min or a local max, you go out, you take the derivative, you see where it's equal to 0, you see where it fails to exist. Those are your candidates. Notice it doesn't say anything about an absolute min or an absolute max. So we're going to talk about absolute mins and absolute maxes right here. We're going to talk about those. We're going to say, okay, what do we do with the closed interval method? So it says this: to find the absolute max and min of a continuous function f on a closed interval. See where the name comes from? A to B. There is a set of definite steps that we follow. We just follow some steps. All right? Step 1. Find the values of f at the critical numbers. Okay. Step 2, find the values of f at the endpoints. Just write these down. I'll draw a picture here and try to bring some clarity to this. Right? That's my job. Your job is to write it down. My job is to make it make sense. 3, the largest value values from 1 and 2 is the absolute max, and I think you know where we're going here. The smallest values are the absolute mins. Okay. So let's talk about this for the picture real quick, just before we start. If we have a graph that goes like this, right, and our closed interval begins here and ends here. Why do we need these steps to find the absolute min and the absolute max? Well, let's take a look at our picture. Right? We've got, this is what we have going on right here. This is our closed interval. The derivative equaling 0 means, right, that the slope of the tangent line is 0, because the derivative is the slope of the tangent line. So we know the derivative is going to be 0 here, because the slope of the tangent line is 0 there. We know the derivative is going to be 0 here, because the slope of the tangent line is 0 there. We know the derivative is going to be 0 here, because the slope of the tangent line is 0 there. And we know the derivative is going to be 0 here because the slope of the tangent line is 0 there. So step 1 says find the values of f at the critical numbers. There is nowhere on this graph, and perhaps I should have made a graph with a corner in it as well, but there's nowhere where the derivative fails to exist. It's continuous, right, and differentiable. So there's nowhere the derivative fails to exist. However, there are 4 places where the derivative equals 0. So, what does this method say to do? It says to identify these, right? Call this x1, call this x sub 2, call this x sub 3, call this x sub 4. Okay, so we identify the critical values. We've got them all identified. And then it says to us, I'll write on this line so it's still visible. It says to find f of x1, right? How do you do that? Well, you plug x1 in. Find f of x2. Go find f of x3. And go find f of x4. Now, if we were to stop there, we would say, okay, one of those is the absolute max and one of those is the absolute min. And it's true. It does work out, by the way, that this is our absolute min. This is the smallest y value in this interval. If we say this goes up to here, to the blue line, then this is clearly smaller. So that would be our absolute min, and we would have found it. This person right here, this would have been the absolute min. However, we would have failed in finding the absolute max. We would have said, this is the biggest y value right here. So this is my absolute max. Clearly not the case. This y value right here is much bigger than that y value. And we did not find that by using just the critical numbers. We didn't find it. Hence, step 2. You've got to test the endpoints. Don't forget to test the endpoints. So in addition to finding these, we really need to also, barely on the screen, but we'll keep it there, also find f of A and f of B, right? And why do we do that? Because in this case, this was my absolute max. And if I hadn't checked my endpoints, I would have never found it. All right. That concludes the lesson, right? The lecture that I'm going to provide to you here. I'm going to do a few examples, right? And this is what I've decided to do during our online learning session here. I've decided that I'm not going to look at the homework problems on this video. On this video, I'm just going to pick some problems and do them, and then I'm going to prepare a second video. It'll be online maybe today, maybe tomorrow. And that video is going to be the video that we use as our examples, homework questions. Before we have our Zoom meetings, which I'm anticipating my first Zoom meeting being maybe next Monday night, just to let you guys know, since you're probably watching this video. I'm recording this on Wednesday, March 18th. Wednesday, March 18th, 2020. The year 2020. All right. So where do we go from here, and what does a typical homework problem look like? Well, I'm going to move down past the conceptual problems in the book, and I'm going to go down to some of the mechanical problems, because I think that's going to be easier for me to explain here on the hover cam, on the dock cam, and with a pen and paper. So I'm going to look at problem number. Let's just look at problem number. Where do we want to start, right? Let's start with problem number 19. Right? We'll start with problem number 19. Problem number 19 says f of x equals the natural log of x, and it says our interval goes from 0 less than x less than or equal to 2. Okay, this is our function. And the instructions say, sketch the graph of f by hand, use your sketch to find the absolute and local maximum and minimum values of f. So they want us to draw the graph of this. And just to self-identify from the graph, right, the absolute mins, the absolute maxes, the local mins, and the local maxes. So they're checking to see if we have a grip on the concepts, right? Do we understand the concepts? Now, the graph of the natural log of x is, of course, something we're very familiar with. The graph of the natural log of x goes like this. It's a monotonically increasing function, has a vertical asymptote at x equals 0, has an x-intercept, of course, at the point x is 1, y is 0, and this is our graph. All right, this is our graph. And here we go again. why did I pick this one? Well, it's on a closed interval from 0 to 2. Right? So we're going from 0, open at 0, right? Open at 0 to 2. We'll just call this, if that's 1, we'll call this 2 here. So our graph stops right here. Right? Now remember, what we're supposed to do here is to get the camera to quit doing this. That's what we're supposed to do. Maybe this is going to be better. So what are we supposed to do? We're supposed to answer questions. Is there a local max? Is there a local min? Is there an absolute max? I know what you're thinking. Stop thinking it. That's not very nice. You're thinking a smarter person would have figured out to turn that light off a long time ago. That's not nice. We don't need to bring that up. So, do I have any or all or none of these, right? That's the question. So we'll start with a local max. Now remember, this is a closed interval, despite the fact that I drew it as open. This is a closed interval at 2, right? At 2. That's the closed interval at 2. Do we have a local max? Now see, I'm stopping so you can talk. This is where you talk. I don't hear you. Yeah, I still didn't hear you. So I'm just going to go on and assume you just don't want to answer any questions today. So how about a local max? Well, the key to the local max, if you remember back to what we said earlier, the key to the local max is we have to be able to put an open interval around that point and say to ourselves, is that the biggest y value in the open interval? And this is one of those trickier kind of questions, those esoteric questions, where because our graph actually stops, right? This graph's not here. I know you see a graph there, but I don't know how you see it because it's really not there. Because the graph stopped at 2. So we cannot put an open interval around there. So the answer to we have a local max, the answer is no. No. Do we have a local min? Well, this goes down forever and forever and forever and forever and forever. So the answer there is no. Do we have an absolute max? Well, the answer there is yes. There is a biggest y value on our graph. Do we have an absolute min? No, we don't have an absolute min. There is no absolute min. All right? There's no absolute min because the graph goes down forever. No. Now, we need to identify and make sure we are clear on what the absolute max is. All right? The absolute max, and this is true for all of these, by the way, the absolute max, the absolute min, the local max, the local min. The absolute max is, and I'm going to underline that a bunch of times because it's very important, is the y value. So if someone were to ask us, what is the absolute max, we would say here, the absolute max is y equals the natural log of 2. All right? It's so important that we understand that because a lot of times we want to write down the absolute max 2 comma ln of 2. Well, that's not correct. The absolute max on every definition you've written in your notes has always said f of c, f of c, f of c. So we have to make sure that we're clear that the absolute max is the y value. Now, they may say, where does the absolute max occur? If they ask that, right, where does the absolute max occur? Well, if they ask that question, the answer to that is, it occurs at x equals 2. So we have to make sure we know the difference between these two questions. All right? What is it? That's the y value. Where does it happen? That's the x value. All right? That's a big deal. Now, what else are they going to ask us to do in the homework? Well, they're going to ask us to do problems that say find the critical numbers. Right? So if I work out a problem like 25, 25 says f of x equals x cubed plus 3x squared minus 24x. Now the directions say find the critical numbers, right? It does not say find the mins and maxes. That's not what it says to do. It says find the critical numbers. So we have to go back to our definition of critical numbers. We have to tell ourselves, okay, a critical number is a place where the derivative equals 0 or fails to exist. So our first step there is to find the derivative. So what do we get? We get 3x squared plus 6x minus 24, which of course factors as 3 times x squared plus 2x minus 8, right? And that again factors as 3 times, and our binomials here are x. This is going to be plus 4, this is going to be minus 2, and it's doing the flashy thing again. So for all of you that were giving me grief because I didn't turn off the light sooner, obviously I didn't fix it. So here we go. That's okay. Like I said, this is round 1, right? We've got more options. So a critical number is a place where the derivative equals 0 or fails to exist. Well, what would we do here? Well, we set f prime of x equal to 0. All right? So that means we take 3 times x plus 4 times x minus 2. We set that equal to 0. Of course, that gets us x plus 4 equals 0, or x minus 2 equals 0. So we get x equals negative 4, or x equals 2. These are our critical numbers. Now, remember what I told you about critical numbers. The most important thing is to check to make sure they're in the domain of the function. Our function is a polynomial. It's defined everywhere. So voila, these are our critical numbers. Okay? Now, how would one take this problem and turn it into an extreme value theorem problem? Right? A problem where it says, find the absolute min. Well, I'll tell you what. I'll just do one of those. I was going to just morph this problem into one of those problems, but instead of doing that, let's just do a separate problem, right? Let's just do a separate problem. It's not like we have anything else to do, right? So, problem 45. All right, so this is an example of the last type of problem you're asked to do in the homework. Problem 45 says, find the absolute max and absolute minimum values on the given interval. So we're going to use the closed interval method here, and we're going to find it. So what does 45 say? 45 says f of x equals x to the 4th minus 2x squared plus 3. All right? And our closed interval that we're working on is negative 2 to 3. So we're supposed to use the closed interval method, find the absolute mins, the absolute maxes, which are guaranteed to exist because this is a polynomial. Polynomials are continuous everywhere. And the closed interval method said if we have a function that's continuous on a to b, we're going to have an absolute max. We're going to have an absolute min. That's what it said. Okay. So what do we start with? Well, we start with finding the critical numbers. That was step 1, right? Step 1 was to find the y values of the critical numbers. So before we can do that, we need the critical numbers. F of x is going to, f prime of x is going to be 4x cubed minus 4x, right? That's where we take the derivative, which factors, of course, to 4x times x squared minus 1, which, of course, factors to 4x times x minus 1 times x plus 1. So I'm just going to skip to the critical numbers. I'm not going to solve this and set it equal to 0. I think all of us can figure that out. Our critical numbers are x equals 0, x equals 1, and x equals negative 1. Now, our job is to find the functional values of those, the functional value of those, right? F of 0, f of 1, and f of negative 1. Don't be the kid that comes, well, no one's going to come up when we take the midterm, aren't we? Because we're not going to be in the same room anymore. But don't be the person who mistakenly plugs these values that we just found back into the derivative. Because a funny thing's going to happen when you plug it in the derivative. You're going to get 0 every time. You don't want to be that person that's like, man, why do I keep getting 0? I guess all my absolute mins are 0. Well, no. You've got to plug it back into the function. Find the y values of the critical numbers. So what do we get for f of 0? For f of 0, we get 3. Right? For f of 1, we get 1, take away 2. That's negative 1. Plus 3. That's 2. Negative 1 to the 4th is 1. Negative 1 squared is 1. So we get 1 minus 2. That's negative 1 plus 3. That's going to be 2. Okay? Now, we don't know if those are absolute mins or absolute maxes. We don't know. Because we have to do step 2. Right? Don't forget step 2. Check the endpoints, right? Check the endpoints. Now our endpoints are x equals negative 2 and x equals 3. So we have to find f of negative 2. Oh my goodness, this is going to take some work. So negative 2 to the 4th is going to be positive 16, right? Positive 16. Negative 2 squared is going to be 4. 4 times negative 2 is minus 8. Plus 3. So we get 16 minus 8 is 8. Plus 3, that's going to be 11. Right? That's going to be 11. F of 3, right, that's going to be even more work. F of 3 is going to be 3 to the 4th. 3 to the 4th is 81. 3 squared is 9. 9 times negative 2 is minus 18. Plus 3. Right? Plus 3. And if we do that, we get 81 minus 20 is going to be 61. Plus 2 is 63. Plus 3, I think we get 66 there. So remember what the closed interval method says. The biggest number off this list is our absolute max. The smallest number is the absolute min. So our absolute max, assuming I did my arithmetic right over here, is 66, and it occurs at x equals 3. Our absolute min is 2, and it occurs twice at x equals 1 and x equals negative 1. All right, so that's going to complete my lecture on section, in case you forgot what we were doing, section 4.2, right? And I anticipate, maybe answering, what I'll probably do is record probably another, this is going to be like an hour and 15 minutes before I wind it up. I'll probably record a few more examples other than these, right? I'll do some more problems for you. And then, I'll send you guys an email or a remind, since everybody's on remind now. I'll send you a remind about, when we can see conduct our first Zoom meeting. All right, hope everybody's doing well. Hope you haven't run out of toilet paper yet. And, well, we got one in the books, right? One in the can, as they say. All right, thank you guys very much. I'll talk to you again on the next video.